This exercise is a lot of calculation, but it's a nice example of how we can actually get a concrete feeling for these theoretical concepts that we've been learning. So the risk-free asset in this situation has value 1 at time 0, no surprise, at time 1, 41 over 40, and at time 2, 41 over 40 squared. The American option, C put, which I shall denote by C for now, because otherwise there'll be a lot of writing of put when it's not really necessary, has value at time 0, given by k minus S0 plus, which is just equal to 2. At time 1, we have to split over whether the value of the risky asset increases or decreases. So if it increases, the value of the American put goes to 7 over 4. If it decreases, this is just, let me just make explicit at least once what's going on here. That's S0 U. That should be S1 U. And now I can't erase. There we go. Plus, just 7 over 4, and C1 D, 11 over 5. At time 2, we need to distinguish between going up and then up and then down and then up, and down or down and then down. The first (23/16), just using the values of S given to us in the statement of the question. Up down has value 2, as does down up. No surprise there, because of course we're just multiplying by U and then by D, and it doesn't matter in which order we do that. And if the value of the risky asset decreases both steps, then the value of the American put goes to 59 over 25. The equivalent martingale measure, Q, which we know exists because we're in an arbitrage-free situation. I didn't this time make that explicit, but we have a condition for arbitrage-free binomial markets, also in multi-period. It's just that D is less than 1 plus R less than U. And we're in that situation. So we do have an equivalent martingale measure. And in fact, the value of Q is explicitly given, this QU, normally denoted by little q, by 1 plus R minus D over U minus D, which in this case is a half, and in this case is also then equal to 1 minus Q, because of course Q is split between U and D, and they have to sum up to 1, so if Q of U is a half, Q of D, which is 1 minus Q, is also 1 half. The Snell envelope of the discounted option, which once again I'm going to neglect to write the put notation, but it is supposed to be there, has value, well, at the terminal time, just has the value of the discounted option, which is the value of the option itself divided by the value of the risk-free asset at that time. Which should, I believe, I think I've written that wrong in my notes as well. That's dividing by the value of the risky asset, not multiplying by it. That's on the event that we go up twice. Well, better, that's not quite, because that's sort of lazy notation. Better to write like this. On the event that the value of the risky asset increases twice, going up and down is of course the same as we just discussed as going down and up. That's 2 multiplied by or divided by the value of the risk-free asset at time 2. And what we calculated for going down twice, 59 over 25. Similarly, the Snell envelope at time 1 is given by the maximum of the value of the discounted option at time 1 and the conditional expectation on the equivalent martingale measure of the Snell envelope at time 2 given f1. So again, it's a random variable, it takes a different value, whether conditional on whether the risky asset increases or decreases in value. My calculation of this was 79 over 41. This is just calculating the conditional expectation given what we know already of the equivalent martingale measure and comparing that to the value of the discounted option. Value of going down is 88 over 41, and doing the same thing but this time at time 0, which of course is not a random variable, will give us a value of 2. Just exactly the same process once again. Therefore, a lemma in the lecture notes, which for me is lemma 5.15, tells us that the arbitrage-free price of the option, which I will now just write that put again, just to remind us what it is that we're talking about, is equal to the value of the Snell envelope at time 0. This is the statement of the lemma, and that is 2, and that is therefore the arbitrage-free price of the option at time 0. The optimal exercise strategy, which we know exists because we're in an arbitrage-free setup, is the random time tau star, which is the first time in our time interval, such that the Snell envelope has the same value as the discounted option price. In this situation, that time is 0. Almost surely. Of course, it need not be equal to just one value almost surely, but when it's time 0, all the processes are deterministic because they are f0 measurable, and so it must have an almost sure value.